Alright, so we're talking about elastic and inelastic collisions. So first question is, what's the difference between elastic and inelastic? Well, when you think about the word elastic, it usually means something that is stretchy, and if you think about like an elastic waistband of your pants, you stretch it out and it goes back to its original shape. So when you talk about elastic collisions, you're thinking about things that when they bounce against each other, they go back to their original shape. And elastic collisions are ones in which the objects bounce. Inelastic is kind of the opposite. There are collisions where things stick together. Now you're going to see words in questions saying things like perfectly elastic or inelastic. In real life, they're not. Most things are not perfectly elastic or inelastic. They're kind of a combination of the two. We are going to assume that all the things we talk about are perfectly elastic, meaning that when they bounce, the momentum is conserved between the two things interacting with each other, and that not only the momentum, what happens to the energy, the kinetic energy is also conserved. So when two things bounce in an elastic collision, they bounce off each other, momentum is conserved, kinetic energy is conserved, and there's no lasting deformation in the items. With an inelastic collision, the objects stick together, there is lasting deformation, the kinetic energy is not conserved, it gets changed into sound, light, heat, and it's also used to reconfigure the atoms of the object. So imagine a car hits a telephone pole. Clearly kinetic energy is not being conserved. That car's coming to a stop. And there's going to be some energy used in reconfiguring the shape of that car as it gets all crunched up. Let's talk about inelastic collisions first. In this type of collision, or an explosion, two objects stick together and move as one. So you've got object 1 plus object 2 for momentum equals both objects together for momentum afterwards. And so you got two cars run into each other and stick together. Car 1 plus car 2 equals both cars together. Then you can also consider explosions. Explosion can be something as dramatic as a cannon or as simple as throwing a ball. So here you get two objects that are together in the beginning and they separate into individuals. This is the same equation. It's just where are they together, where are they separate. So you're looking at a cannon. You've seen a pirate movie. In the cannon, in the movie they fire the cannonball out the cannon. The cannon itself rolls backwards. This is to conserve momentum. You see initially they're together, moving at a common velocity. And in most cases, they're not usually going forward or backward to begin with. It goes off. Because they're moving together here, they have a common velocity, and most likely they're not moving. Your initial momentum is 0. That means your final momentum must add up to 0, meaning the cannon is going to have a negative momentum. The cannonball is going to have a positive momentum. So the cannon and the cannonball have equal and opposite momentum so that it can be conserved. Now the cannon, we know, is a lot bigger than the cannonball. That's why the cannon goes slower and the cannonball goes faster. This idea right here is often described as recoil. When people are shooting a gun, the gun kicks backwards. Well, that's why, because momentum is being conserved. If you were in class, you remember I had a little video of a guy shooting a gun and the gun kicks back and knocks him down on the ground. Because the momentum of that bullet was very large, and it in turn pushed back that gun back a lot into the guy's shoulder. And he was a fool and didn't know what he was doing. So inelastic collisions, the big thing here is they stick together or they start together, and the momentum is conserved. Kinetic energy is not conserved here. Because, especially think of like the cannon. Initially, the cannon is sitting still. It has no momentum whatsoever. Or no momentum, which it does. It has no kinetic energy. So for that to bounce out, you'd have to have no kinetic energy afterwards if you're conserving it. Well, that doesn't work. The energy is bound up in other ways here. So we have an example here where we have two cars colliding. To set this problem up, you're going to take the mass of the blue car, and it's traveling at 22 meters per second. It's going to run into the red car from behind, the big red car, and it's not moving. Well then, afterwards, they're going to move together. So you want to add their masses together times the final velocity of both of them. And you can figure out how fast they're going afterwards. When this kind of thing happens, you end up getting a blend of velocities a lot of times. So it's going to go forward, but slower. And then there's a homework assignment associated with this. And you just practice that over and over again. But let's talk about elastic collisions also. So an elastic collision, you recall from a couple minutes ago, is when the two things bump into each other and they bounce off of each other. Think of bumper cars here. Think of a billiard ball. These things all bounce off each other very easily. Well, in these collisions, momentum is conserved. So the momentum of the red car plus momentum of the blue car equals momentum of the red car plus momentum of the blue car. The total over here equals the total over here. They might share differently on both sides, but the totals are indeed the same. Well, not only momentum is conserved, but also kinetic energy is conserved. The total kinetic energy here is equal to the total kinetic energy over here. And that's our last two topics. I'll show you the review questions in case you don't have those written down and you want to write them down before you look at the videos on how to do them. There's review questions. Alright, good luck.